Welcome to solverfy.
Hi there. So for this problem, we are told to consider enough of the electric dipole moment matrix elements for the charged particle in an infinite square well potential using the eigenfunctions of section 6.8 to see if there is a selection rule for this system, and if so, to determine what it is. So we know that the infinite square well eigenfunctions, apart from the not needed normalization constants, are the following. So those are phi of x is equal to the sine of n times pi times x, and this divided by a for n even. And for n odd, we have the following expression: cosine of n times pi times x, and this divided by a for n odd. So it is required to evaluate this function, the probability function. So that will be the integral of the conjugate of the wave function at the final quantum state times the e times x, and this times the wave function and the eigenfunction for the initial state integrated over x. And we know that this is proportional to doing the integral from -1 divided by 2 times a to 1 divided by 2 times a of the final state times x times the initial eigenfunction integrated over x. Now, in the following, we are going to do the following change, that u is equal to n times pi times x, and this divided by a. And also, we're going to denotate n and m, the two levels. Now, for the first case in this, we're going to do the transitions between even and levels. So in that case, we will have that the probability is proportional to the integral from -1 divided by 2 times pi to 1 divided by 2 times pi of u times the sine of n times u times the sine of m times u integrated over u. So in this case, as you can see, we have the sine function in an interval that is not symmetric. So with that, we will obtain that this is just simply equal to 0, since the integrand in here is odd. Now, for the second case in here, we're going to have that the transitions between odd and levels. And for that, we're going to have that the probability is again proportional, but in this case to the integral of -1 divided by 2 times pi to 1 divided by 2 times pi of u times the cosine of n times u times the cosine of m times u, and this integrated over u. And this is equal to 0 again, because the integral in here is odd. Now, with that said, we came to the last case. In this last case, we're going to have the cross terms. So these are going to be transitions between odd and even and level. So we're going to have that the probability is proportional to the integral from -1 divided by 2 times pi to 1 divided by 2 times pi of u times sine of n times u times the cosine of n times u integrated over u. So this is equal to 2 times the integral from 0 to 1 divided by 2 times pi of u sine of n times u cosine of m times u integrated over u. Now with this, we are going to obtain from these integrals that this is going to be 1 divided by 2 times the sine of 1 divided by 2 times pi and of course this times n minus m, and this divided by n minus m to the square. So this plus sine of 1 divided by 2 times pi of n plus m, and this divided by n plus m to the square. Now the other terms in here are going to be minus pi divided by 4 times, well, in this case, oh, sorry, this is for this. And for the last one in here, we will have it. This is pi divided by 4 cosine of 1 divided by 2 times pi times n minus m, and this divided by n minus m, and this plus the cosine of 1 divided by 2 times pi times n plus m, and this divided by n plus m. Now, evaluating the final integral in here, and so clearly the above is not 0 for n even, not 0 for n even, for n even and m odd, m odd. Hence, transitions are permitted only between levels such that one is odd, one is odd, of odd n, and the other even n. Example, the transitions rules are going to be different from 0 when n is equal to, the change in the quantum state is plus or minus 1, plus or minus 3, and plus or minus 5, and so on. So that's a solution for this problem. Thank you.